except the omega. The omega is not a vector. So we know our length. So we know our B with respect to A. We know our B with respect to A as well. We found AB, omega AB already, or I'm sorry, we're given AB already. So we would know all of these, then we can find AB. In this problem, what is alpha AB? We're going to see later that alpha AB is going to go to 0, and that's because omega A is given as a constant 6 radians per second. So here we can find AB. So moving along, we need to now compare B and C. So we will have AC equals AD plus alpha BC cross RC with respect to B minus omega BC squared RC with respect to B. Again, all of these are vectors except omega BC. This equation is going to be your third equation. AC, C is also a part of rigid body CD, so we can say, and it's in pure rotation. So we don't have a linear component. There will be no AD. We can just go straight to alpha CD cross RC with respect to D minus omega CD squared RC with respect to D. And this will be your equation 4. If you set equation 3 equal to 4, you will get an answer for alpha CD and alpha BC. And that is what our problem is asking us for. So just by taking a little bit of time in the beginning of your problems to work out a method, you can kind of keep your mind in order when you're going through these types of problems, because again, there's so many equations. So when the steps that you're supposed to take. So now that we have our method, let's move on to the actual solution. So moving to the solution, we'll take our first equation, VB equals omega AB cross R. So we have VB equals omega AB cross RB with respect to A. Omega AB is given to us as -6 in the K direction. RB with respect to A, so that's going to be a vector going downwards like that. So, and the radius is 0.3. So this will be 0.3 negative in the J direction. If I do -6K cross -0.3J, I will get a velocity for B as -1.8 in the I method. There is another method. So in this one, you would do 0, 0, -6, and then you do 0, -0.3, and 0. There is another method. If you write down I, J, K, and you go in a circle in the clockwise direction, if I do I cross J, I get K. If I do K cross J, I get -I. This is really helpful, but just remember that if you do -I cross J, I cross J is positive, but you still have to follow sign convention, so that's actually a -J. Quick side note. Okay. So whichever way you do the cross product is fine. You'll get the same answer either way. So here we have VB is -1.8. So we are done with our first equation. Now we're going to move to our second equation, which relates point C with point B. We'll do that in blue. So we have VC equals VB plus omega BC cross RC with respect to B. We know that VB we just calculated as negative 1.8. So we can substitute that in negative 1.8 in the I direction. Omega BC is in the K direction. And RC with respect to B. RC with respect to B is going to be a position vector that looks like that. That means that it's 1.5 in the I direction. So this is going to be 1.5 I. This will yield VC is equal to VC is equal to negative 1.8 I plus 1.5 omega BCJ. This is our first equation. Now we move on to our second equation where we relate point C to D. It's in pure rotation, so we can write, let's use color. Let's do orange. We can say that VC is equal to omega CD cross RC with respect to D. Omega CD is an unknown, but we do know it's in the K direction. And RC with respect to D, let's go ahead and find that. RC with respect to D will look like a position vector like this. So we will have an I component that's positive. We'll use the projection. It will be 0.6 cosine 60 in the I plus 0.6 sine 60 in the J. RC with respect to D is going to equal 0.3 I plus 0.52 J. So let's go ahead and plug that in. We will have, so this here is 0.3 I plus 0.52 J. Doing this cross product, we will get that VC is equal to 0.3 omega CDJ plus 0.52 omega CDI. Our second equation. Now we need to set equation 1 equal to 2. And we can write that out. We have negative 1.8 I plus 1.5 omega BC J equals 0.3 omega CDJ minus 0.52 omega CDJ. By setting equations 1 equal to 2, you get one really large vector equation. But this vector equation has 2 components. So now you can separate the I components with the J components. So we have our I's will be negative 1.8 is equal to negative 0.52 omega CD. This will give us our value for omega CD, 3.5 radians per second. Now we can look at our J components. We have 1.5 omega BC equals 0.3 omega CD. Omega CD we just calculated as 3.5. This will yield omega BC equals 0.69 radians per second. So now, looking back at our method, because we've done a lot so far, let's just check in. We've done all of these successfully. We have completed our entire velocity methodology because we ended up with a value of omega BC and omega CD. Now we are ready to move on to our acceleration. So let's go ahead and fill out on this side. Omega BC is 0.69 radians per second. And omega, oops, just kidding. Oh no, that's right. Omega CD is 3.5 radians per second. So now we're on this side of our methodology, starting again back at rigid body AB. So if I compare A, B equals, again, B is in pure rotation around A, so we do not include the translational term, just the rotations. So we have alpha AB cross RB with respect to A minus omega AB squared RB with respect to A. This is your translational component. This is your normal component. This is also known as your centripetal acceleration. Because in the beginning of the problem, we are told that omega A is a constant 6 radians per second, which term goes to 0? If you said the alpha term, you're correct. So this whole term goes to 0 because the derivative of omega is alpha. But if omega is a constant, this will equal a 0. Note that if we are looking at a point on a circle, the velocity is always tangent to the circle and in the direction of motion. However, acceleration occurs in both directions. You will have a tangential acceleration and you will have a normal acceleration. So if omega, which if you recall back in my lecture of the coordinate systems, we talk about the equations for AN and AT. Well, AN is omega squared R. This is given to you as 6. So AN is not 0. AT does have an alpha in it. So that part does go to 0. So please do not, read the question, and just because it says constant angular velocity, don't just assume that the acceleration is 0. Only part of the acceleration will be 0. Okay, now that we have that cleared, we can move on. So AB, we are given omega AB is 6. RB with respect to A was negative 0.3 in the J direction. So AB is going to be equal to 6 squared times negative 0.3. And that is going to equal 10.8 J. And that's in the positive. So our acceleration vector is going to be going in the normal at 10.8. This is in the normal direction, but remember we're working in Cartesian coordinates, and we already defined the up as J or Y, and then positive X or I. So this is 10.8 in the J direction. Okay, so now we finished our first equation here. Now we can move on to our equations that relate point C to B and C to D. So first, working with rigid body BC, we have that AC equals AB plus alpha BC in the K direction cross RC with respect to B minus omega BC squared RC with respect to B. We know that AB is 10.8 J. I don't know alpha BC, I'm looking for that. RC with respect to B is 1.5 I. 1.5 I. Omega BC we found earlier, and we said it was 0.69. So this is 0.69. RC with respect to B, again, is 1.5 I. So if we solve this out, we are going to get that AC is equal to 10.8 J plus 1.5 J, and you're doing K cross I, so that's a positive. Oops, it's going to be 1.5 alpha BC J. And then you're going to have 0.69 squared times 1.5 I. That should give you 0.71 I. And this becomes your equation 1. To get your equation 2, we have to compare points C and D. So we will come up with our next equation. AC is equal to, C and D is undergoing pure rotation, so we just have the rotational components. We'll have alpha CD, which is in the K direction, cross RC with respect to D, minus omega CD squared RC with respect to D. All right, we have omega CD we found earlier, and we said that it was 3.5. 3.5. RCD we also calculated earlier, and we said was 0.3 in the I plus 0.52 in the J. So let's go ahead and rewrite this out. We have AC is equal to 0.3 alpha CD. K cross I is J, and that's a positive. And then you have 0.52 alpha CDI. K cross J is I. It's going in the backwards direction, so we put a negative. And then we have minus 6.37 J. This is going to be your second equation. Now we are ready to set equation 1 equal to 2. If we look at our I components first, go to your first equation. You only have one I, so you can write negative 0.71 is equal to. Go to your second equation, look at your I's. You have two terms, so it is going to be equal to negative 0.52 alpha CD minus 3.68. This equation is going to yield an alpha CD equal to negative 5.7-ish radians per second squared. That is your first answer. We're not done yet, though. So let's go ahead and look at our J components. In the first equation, you have two components that have a J in it. So you are going to write 10.8 plus 1.5 alpha BC is equal to, and then in your second equation, you will also have two terms. So let's write those out. We have 0.3 alpha CD minus 6.37. And if you plug in alpha CD here, this equation will yield an alpha BC of negative 12.59 radians per second. So that is our second answer. Now we have completed what the question is asking for. And if you look back, I think that this method is pretty useful, okay? You draw your three-body diagram, you understand what the mechanism is doing, you write down your method, which includes all of the equations that you plan on using. That way you're not going to get lost midway through your problem. And then you just start working it out. Okay, so let's do another example. Okay, example 2. In example 2, we are again trying to find the angular velocity of bar BC and CD. This time we have 3 rigid bodies. Bar AB is in pure rotation about A. C is in pure rotation about D. And bar BC is undergoing planar motion. We are given that AB has an angular velocity of 10 radians per second in the counterclockwise direction, and we are given that the angular acceleration is in the clockwise direction, 300 radians per second squared. So we are given, once again, kind of like normal, and you're going to see this trend throughout dynamics, we are given everything about the first bar, but we want the information in the later bars, right? So let's go ahead and write down our method. We are going to start with, even though we are given the angular acceleration of bar AB, we're still going to start with the velocities because we do not know omega BC or omega CD. So even though we're given a little bit more information in this problem than the last one, we will need to still find those omegas before moving on to find our alphas. So for our velocities, we will do VB equals, this is in pure rotation, so we'll have omega AB in the K direction cross RB with respect to A. Then you will have, you will relate points B and C. Velocity of C equals velocity of B. BC is in planar motion, so you will have the translational term, plus omega BC cross C with respect to B. That will be your first equation. So this is equation 1. Your second equation is to get another equation for velocity of C. To do that, we're going to relate it to point D, which is C is in pure rotation. So you will have omega CD cross RC with respect to D. This will be your second equation. If I set 1 equal to 2, that will yield omega BC and omega CD. I can then use these as inputs into my acceleration equations. So I'll do the same thing. I'm going to find my relation between A and B for acceleration. So I have acceleration of B equals, again, it's in pure rotation, so I'm not going to have a translational term. Now, though, since we're in acceleration, we will have two rotational terms. So I will have alpha AB cross RB with respect to A minus, we are in planar This is a planar mechanism. We are not in 3 dimensions, so we can use the shorthand omega AB squared RA with respect to B, with the following being vectors, noting omega is a scalar. Now we can relate points B and C. So we have the acceleration of C equals the acceleration of B plus alpha BC cross RC with respect to B minus omega BC squared RC with respect to B. This is your third equation. Now you have to develop your last equation, which is going to get a second equation for AC. And we will get that second equation by looking at bar CD, which is in pure rotation. So you will have alpha CD cross RC with respect to D minus omega CD squared RC with respect to D. This is your fourth equation. If I set 3 equal to 4, that will yield alpha BC and alpha CD. Now that I clearly understand what my mechanism is, what my problem is asking, and I set up my method, I can go ahead and solve with confidence. All right, so let's go ahead and start the solution. So we will start with our first equation. Velocity of B is equal to omega AB. Omega AB is given as 10 radians per second in the counterclockwise direction. So that is 10K cross RB with respect to A. RB with respect to A. So that will look like a vector, a position vector like so. It will be positive 2 in the J direction. K cross J gives me an I, and it will be negative I. So velocity of B is going to be negative 20 in the I. I want to go ahead and check that and see if it makes sense. I am rotating in the counterclockwise direction. Velocity is always tangent to the curve and in the direction of motion. So that to me says that that makes sense and I can move forward. Okay, equation, the second one listed, our first velocity for C equation is going to be VB negative 20I plus omega BC in the K direction cross RC with respect to B. RC with respect to B is a position vector that looks like this. It is going to be purely in the I direction, 2 feet. So we will have plus 2I. And this is going to be VC equals negative 20I. We'll have 2 omega BC. K cross I is J, and that should be a positive. Moving to our next one. So this is equation 1. Then we'll do VC equals, we're going to compare it to D. So we have omega CD cross RC with respect to D. So that position vector will look something like this. It will have, so RC with respect to D will have a negative I component. So we'll have 2I, and it will have a positive J component. So this will be negative 2, positive 2. VC equals CD, K cross J is K cross I. So is a J. It starts with a negative. And then you have 2 omega CD, K cross J is I. And that should be a negative. Okay, this is your second equation. Now we are going to set 1 equal to 2. So if we set equation 1 equal to 2, we have negative 20I plus 2 omega BC equals negative 2 omega CD J minus 2 omega CDI. This is one large vector equation with 2 unknowns. So to solve for the 2 unknowns, we're going to break up the components. We will solve first by equating I terms. We have negative 20 equals negative 2 omega CD. This yields a value for omega CD as 10 radians per second. And if we do the same thing with the J components, we have 2 omega BC equals negative 2. Omega CD is what we just calculated. That's going to be 10. Negative 2 times 10 is negative 20. Divided by 2 is 10. Negative 10. So we have omega BC equals negative 10 radians per second. So we can kind of make sure we're bookkeeping. So go back to your methods part. And we can say that omega BC is equal to negative 10 radians per second. And omega CD is equal to positive 10 radians per second. So now we are ready to move on to our acceleration equation. Our first acceleration equation is going to compare points A and B. AB is equal to alpha AB. Alpha AB is given to us. It is going in the clockwise direction for 300. That means that we are going to plug in negative 300K cross RB with respect to A, which is 2J, minus omega AB. Omega AB was given to us as counterclockwise, so positive 10 radians per second. So we have 10 squared times 2J. So this gives us AB is equal to 300 times 2. So we have 600. K cross J is a negative, but you already have a negative here, so it's going to be a positive I. Then you have a negative. 10 squared is 100 times 2 is 200 in the J. That gives us our first acceleration equation. Moving on, we can now plug AB into our first AC equation. AC is equal to AB, which is 600I minus 200J, plus alpha BC cross RC with respect to B, which is going to be 2 in the I, minus omega BC. Omega BC, we found that earlier, which is negative 10 radians per second. So we have negative 10 squared times 2I. Cleaning this up, we have AC is equal to 600I minus 200J. Then we have 2 alpha BC. K cross I is J, and that's a positive. Then you have negative 10 squared times 2, which gives a negative 200I. All right, that would be our equation 3. Writing out our second equation for AC, we will use our fourth equation over here in our methods. We have alpha CD cross RC with respect to D. We said earlier that that was -2 in the I and +2 in the J. Minus omega CD, we found that earlier to be +10. And we'll multiply that by -2. So we have an equation, AC is going to be equal to K cross I is J. That's going to be -2 alpha CD. K cross I again, cross J, excuse me. K cross J is -2 alpha CDI. 10 squared is 200 times -2. This is going to be a +200 in the I and a -200 in the J. This is your fourth equation. Now I am ready to set equations 3 equal to 4. By setting 3 equal to 4, again, we get one really long vector equations with 2 components, an I and a J. So we're going to break up those components. First, let's go ahead and look at the I component. In equation 3, you have 2 I components. So we have 600 minus 200 equals. In the fourth equation, you have 2 I values, -2 alpha CD plus 200. This will yield a value of alpha CD equals -1 radians per second squared. And if I do the same thing for my J components, I go back to my third equation. I have a J component here and one here. So I have -200 plus 2 alpha BC is equal to, I have one here and one here. I have -2 alpha CD minus 200. This will yield a value of alpha BC as +100 radians per second squared. Okay, that is your answer. Give it a big box. So you have one bar, you have bar CD that is decreasing in speed or in acceleration, and you have bar BC that is increasing. That is example 2. Why don't we go through one more example? All right, our third example, I went ahead and kept up our methodology from the previous example just to kind of show you that it's well, hang on, I'll show you why in a minute. First, let's look at the problem. Here we have two rigid bodies. One rigid body is OA, and A rotates about O in a pure rotation. AB, this is a planar rotation, but B is constrained to only move in the translational direction. And our question is asking us to find what VB is. No, I'm sorry, it's asking us to find what the acceleration of B is. So we are given the angular velocity and the angular acceleration of our first rigid body, OA. We are also given the angular acceleration of the bar AB. So when you look over your methodology that we usually use when trying to find angular accelerations or linear accelerations, we can see that sometimes we don't have to use the velocity portion. A lot of times I see my students on exams, if I give them a problem and I actually give them the information here, they still repeat this step. Don't repeat the step. You don't need to. I'm actually giving you this portion. I'm only testing you on the acceleration part. So when we do the velocity part, I'm telling you to set 1 equal to 2 to give you the omegas. Well, the problem already gives it to you. So that means that in this problem, I do not need any of this method. I only need my acceleration methodology. Okay, with that said, let's take a look at what we can use. Let's think this out. I'm given my omegas, so I'm going to immediately go to my accelerations. This point O is an external pin. That means that the acceleration, the linear acceleration of O is 0. So I can write A equals AO. AO is going to be 0 because A is in pure rotation about O. So we'll have alpha AO cross RA with respect to O minus omega AO squared RA with respect to O. We are given alpha AO. Alpha AO is 5 radians per second squared. The position RA with respect to O will look like a vector like this. AO is a 3, 4, 5 triangle. So that means that the projection on the X will be -3 in the I, and the projection on the Y will be 4 in the J. We are also given omega AO. That is -10 squared, and you will use the same RA with respect to O, which is going to be -3 in the I, +4 in the J. So I know everything in this equation. Next, all I have to do is say AB, which is what I'm looking for, is equal to the acceleration, linear acceleration of A plus alpha AB cross RB with respect to A minus omega AB squared RB with respect to A. I'm going to plug this one right in, and I will be able to then find the, because I know omega AB. Now I'm not given this, but I am given a clue about this one. The linear acceleration of B, it is stuck in this slot. That means that the acceleration is limited to the I direction. And since this is a vector equation, this will be I. So you'll see that even though you have two unknowns here, if you break up this vector equation into I and J, you will be able to solve for both unknowns. So why don't we go ahead and work this out? Let's take the acceleration of A. Acceleration of A is equal to 5K cross -3, 4 minus -10 squared -3, 4. Okay, so working this out, we have acceleration of A is, so we have 5 times 3, -3. We're gonna have -15I minus 20J minus 10 squared times -3. So a positive 300I. 10 squared times 4, we have -400J. And let's go, we can actually simplify this. So we can say that A is equal to, combining our I terms, we have 285 in the I direction, and combining our J terms, we have -420J. We can go ahead and plug that in right here. So we have AB is in the I direction. It equals 285 in the I minus 420J plus alpha AB, we don't know. RB with respect to A, let's look at that. So we have RB with respect to A. RB with respect to A is going to look like a position vector like this. So it will be positive in the I, negative in the J. So RB with respect to A will equal the positive X component, 12.4I, and minus the J component, which will be 4J. So we can add that in. And if we do the cross product, we should get 12.4 alpha AB J plus 4 alpha AB I. And then our last term here, omega AB was given to us in the problem as negative 2.4. You're going to square this, so that becomes a positive. You're going to multiply it by our position vector, which is 12.4 in the I and negative 4 in the J. By doing this, you should get 72.6I plus 23.4J. In this problem, we have one gigantic vector equation with two unknowns. We have our unknown of alpha AB and our unknown of AB. By taking this vector equation and separating its components, we can solve for both of those unknowns. So let's go ahead and do that. Let's separate, let's solve the J components first this time. And that's because there's 0 J terms here. So I can say 0 equals negative 420 plus 12.4 alpha AB plus 23.4. So this is going to give me an alpha AB of, I'm going to add the 420, subtract 23.4, divide 12.4, and I should get 32 radians per second squared. Now I can look at my I components. My I component is going to be A, acceleration in the B equals 285 plus 4 times 32, what we just found, minus 72.6. And this should give you an AB value of somewhere around 340. And that is going to be inches per second squared. Okay, so that is 3 examples. I hope that you kind of understand what is going on. I know that it's a lot. I know that it's really, really long, and I know that your brain is probably like, what is going on? But the best way to get a handle on these types of problems is to practice. And again, I urge you to set up the method to understand what points are you comparing. Because remember, you can only compare points on the same rigid body to get unknowns of the next. All right, I hope that helped. If you like it, give this video a thumbs up and consider subscribing. Thank you so much. See you next time.